We can trace a direct line from the biological compounds that feed our crops to lethal synthetic lattices. The chemical origins are identical. These physical contrasts originate from a single vertical column on the periodic table, group 15, known as the pictogens. The elements in this specific column constitute much of our physical reality. Nitrogen fills our skies. Phosphorus acts as the structural connector in our DNA. Arsenic provides the high-speed processing power for modern satellite technology. This presents a specific chemical challenge. A single vertical group produces unreactive gases, combustible biological building blocks, semiconductors, and dense heavy metals. Every element here shares a specific quantum architecture, an ns2 np3 valence shell with exactly 5 outer electrons. Moving downwards, principal quantum numbers increase, atomic mass grows, internal shielding thickens, and the atomic radius expands, pushing the valence structure further outward. By tracking this single metric of expanding atomic radius, we can predict exactly how these elements will behave and manipulate their structures for specific technological needs. At the top of the column sits element 7, nitrogen. Here, the atomic radius is at its smallest. Because nitrogen atoms are physically small, they get close enough for their atomic orbitals to overlap perfectly. They share 3 pairs of electrons, forming a highly compressed triple bond. Breaking this configuration requires immense dissociation energy, nearly 1,000 kilojoules per mole. That microscopic strength dictates its macroscopic reality. Because it remains stable and resistant to reaction, diatomic nitrogen exists as an unreactive gas, making up 78% of Earth's atmosphere. When compressed and cooled below -196 degrees Celsius, it undergoes a phase change into a cryogenic liquid. Because the triple bonds remain intact but tightly packed, liquid nitrogen rapidly drains thermal energy from anything it touches, freezing matter on contact. To utilize nitrogen for life, industrial processes must force that triple bond apart. The Haber-Bosch process applies high heat and pressure to break the bond, fixing the nitrogen into ammonia to create crop fertilizers. Nitrogen's applications, from atmospheric stability to agriculture, are a direct consequence of the strength of its microscopic triple bond. Descending one period brings us to element 15, phosphorus. The addition of a full inner electron shell increases the atomic radius. As the radius increases, the size of phosphorus atoms physically blocks them from getting close enough to overlap their p orbitals. A stable triple bond is impossible. Instead, the atoms link outward, forming single-bonded network solids known as allotropes. These single bonds are under significant structural tension. That physical strain causes red phosphorus to spark the immediate combustion of a matchhead. When phosphorus bonds with oxygen, it forms a phosphate group. This 3D wireframe illustrates its rigid tetrahedral geometry. It links with sugar molecules to construct the twisting outer backbone of DNA inside every living cell. The increased atomic radius shifts the element from a stable triple bond to strained single bonds, creating a reactive biological building. The descent brings us to elements 33 and 51, arsenic and antimony. This zone is the metalloid boundary, where electrical conductivity begins to change.
Inner electron shielding pushes the outermost valence shell further from the nucleus. Consequently, the energy required to remove an electron drops. This creates a band gap, the energy barrier between a full valence band and the empty conduction band. Arsenic possesses an intermediate band gap. It acts as an insulator under normal conditions, but with a specific input of voltage, electrons jump the gap, making it a semiconductor highly efficient for high-frequency electronics. When alloyed, it produces gallium arsenide wafers. This specific semiconductor lattice provides the efficiency and signal speed required by modern satellite technology. At element 51, antimony, we find a heavier metalloid with a larger radius, producing distinct protective behaviors. Antimony acts as a chemical flame retardant, engineered into modern textiles and safety materials. During a fire, combustion relies on a chain reaction of reactive free radicals. Antimony compounds vaporize into the flame, intercepting such radicals and breaking the chemical chain reaction. Beyond fire safety, its electron mobility is currently being tested for use in next-generation electronic and memory technologies. By utilizing the intermediate band gaps created by increasing atomic mass, engineers bridge the divide between chemical elements and computing hardware. Crossing the boundary lands on element 83, bismuth. At this mass, the element operates as a post-transition metal. This 3D representation visualizes bismuth's metallic lattice. Its distant valence electrons enter a delocalized state, pooling into a shared structure. Yet its specific electron configuration results in extreme diamagnetism, actively repelling external magnetic fields. Those subatomic properties manifest physically in this stair-step macroscopic crystalline structure, where the crystal grows more rapidly on its outer edges than its center. Because of its heavy mass and non-toxic properties, bismuth is used in precision science and manufacturing as a replacement for lead. Finally, we reach the bottom of group 15, element 115, Moscovium. This is a synthetic, super-heavy element. The immense mass of Moscovium's nucleus drags its innermost electrons inward, forcing them to orbit near the speed of light. This internal kinetic energy destabilizes the atom. Recoil forces between protons lead to rapid atomic decay and a short half-life. Scientists synthesize Moscovium to probe the limits of stability and map the theoretical heavy edge of the periodic table. At the base of the column, the internal mass becomes so great that metallic properties collapse, unable to maintain physical cohesion. Viewing group 15 in its entirety reveals a consistent mechanical logic, from nitrogen down to Moscovium. This vertical heat map tracks the structural gradient. We move from a non-metal gas through solid networks, across the semiconducting metalloid boundary and into dense metals. Across this vertical group, the expanding atomic radius is the primary metric dictating its physical properties. From atmospheric nitrogen to the backbone of cellular DNA and the architecture of satellites, all follow this underlying chemical logic. Each material we see represents a mathematically predictable outcome of quantum mechanics scaling up to our physical reality. Truly understanding advanced materials requires looking past isolated elements to recognize how periodic trends define the physical behavior of the matter around us.